We are at our last lesson for this unit. I know that our workbook has one more lesson in there, but we are going to skip it for now and come back to it at another time in a different unit. So today we're talking about function composition. And this is where we are combining functions. I don't know if any of you have seen the movie like Inception, where there's like a dream within a dream. Well, today we're going to talk about functions inside of functions, and so on. So we can combine functions by any methods that we talked about in our last lesson. Today we're going to talk about composition specifically, and that is if we have two functions, here is f and here is g, then for any number in the domain of g, we can compute g of 3 and then use that output to find f of g of 3. So what we are doing is we take our input, so our x values, and we put it inside the g function, so g of x. And then whatever g of x equals, which is some value for y, we are going to take that value and then input it for f and calculate the function f using the y value from g. And this is why we have this notation. It's f of g of x, meaning g depends on x and f depends on g. So when we do this notation, the shorthand notation for this is outlined here with a small empty circle or empty dot, f of g. And this reads that f is made up of g, or f is composed of g. And the domain of f of g consists of those x's in the domain of g whose ranges are also in the domain of f. And it's a bit wordy here, but essentially this is what we're saying. We're taking the x values in the domain of g. We are putting them into the function g, and what we get out of here are the y values from g. Well, the y values from g then become the x values for f. And when we put them into the function f, we get y values from the function f. So when we talk about the domain, we need the domain, the x values that we choose, have to work for the function g, and the y values that come out have to work as x values, so as the domain for the function f. So it's kind of one inside the other. That we are looking for essentially an overlap. All the x values that can go into g to create y values that will then go into f to create our final y values, right? So the formal definition is this: the composition function of two functions f and g is defined by f of g of x, or sometimes you'll see it in this notation where g of x is inside the f of x function. For all x's in the domain of g, such that g is in the domain of f. So we want one to be inside the other. Okay, so let's take a look at an example. Examples are always a better way for us to get our brains around some new and strange vocabulary as well as some new ideas. So the first letter that you see will be the outside function. So this is saying f of g of x, meaning g depends on x and f depends on g. So this means if we take our function f of x, which is 1, whoopsie, equals 1 minus x squared. right? Because I have an x squared here. But instead of writing x, f depends on g, so I'm replacing x with the entire function of g, 2x plus 3 all squared. And then you can expand this and simplify this. This would be 1 minus, let's see, 4x squared plus 12x plus 9. And then if I distribute the negative, this would be minus 4x squared minus 12x minus 9. And then I'm going to write it with our highest degree first, because this is the polynomial, right? So I do the one with the highest exponent first, minus 12x. I collect like terms where I can, so positive 1 minus 9. This gives me minus 8. And so this is f of g of x right here. Okay? And we can do this in any order that we like. So here's another example, g of f of x, meaning now we're going to start with the g function, which is this, 2, and instead of x, I leave space, plus 3, because in that space, I'm going to put f. And this pencil's a little bit too thick. Here we go. So f is 1 minus x squared. So 1 minus x squared is going to go in here. And when I distribute, this is going to be 2 minus 2x squared plus 3. The 2 and the 3 can combine. So this is going to be negative 2x squared plus 5. And this is the function g that depends on f, which depends on x. And there you go. So you'll notice that these are not the same, right? So order matters. So when we're looking at this notation, the first letter is the outside, your starting function, and you're going to leave space where you see the x in the starting function, and you're going to substitute the second function in the line. All right, let's take a look here. If we have f is x squared and g is 2x minus 1, then we are going to find f of g of x. And now you'll notice here they've given us a specific value. So they want us to evaluate what is f of g of negative 2. So there's two ways you can do this. The first method, you can set up the f of g equation first. So the f of g of x equation would be f is x squared, so bracket squared, and g is 2x minus 1. So you can set it up this way, and then you can substitute instead of x, you're going to put in now negative 2, because that's the number they've given us here. And you can say 2 times negative 2 minus 1 all squared, and then you sort it out. So this is negative 4 minus 1 all squared. This is negative 5 all squared, so this is 25. The other way that you can do it is by saying, take the inside function, g of negative 2. Solve that. And say, okay, g of negative 2 is 2 times negative 2 minus 1. This is going to be negative 5. Then put it inside the f function. Now, f is x squared, so what I'm looking for is negative 5 all squared, which will end up with the same result. So do two different methods. It doesn't matter which one you use. Sometimes this method is easier because you're just dealing with one function at a time, and you're going to find the number, put it in the next one, find the number, put it in the next one for how many ever compositions you have. And if you have pretty simple equations, like this was a pretty simple example, you could do it this way as well, and both of them will give you the same answer. Just sometimes one is easier than the other, so use your judgment there. All right, example 3. Okay, here we go. F of x is x squared minus 1. G of x is the square root of x. And we are asked to find the function f of g and the domain, and we're being asked to sketch a graph. So this is a little bit more complex. So we're not given a number here. In example 2, we were given a number that we could evaluate for an answer. So in example 3, we're just simplifying the function. So let's start with f. And we're going to say, okay, this is something all squared minus 1. So f of g is putting the square root in here. Now, it's going to be really, really, really tempting for some of you to say, oh, I know what that is. The square root of x squared, the squared and the square root undo each other. So this is just x minus 1. And you would be partially correct. Remember that when we have a square root of something, we can have two possible outcomes. We can have a positive number and a negative number, right? So when we take the square of a square root, right, we're squaring it like this, which is always going to end up giving us a positive number. Now, do you remember what's the function that no matter if x is positive or negative, always gives us a positive? If you don't remember, it is the absolute value function. Another way to describe the absolute value is the square root of something squared, because it could be positive or negative, but then you square it and it always gives you a positive number. So I'm just going to erase all this. So we have a slight modification here. This is the square root, or sorry, the absolute value of x minus 1. So anytime you have a square root all squared, this is forcing the outcome to be positive, but you know that the input could be positive or negative, and therefore this is the absolute value function. Now, the absolute value function we know looks like a V. However, we see a translation here. This is telling us that the absolute value function has been shifted down 1. So if I'm graphing it, 3, 4, 1, 2, 3, 4, 2, 3, 1, 2, 3, we have shifted the vertex down 1. All right. And this is our V. That's what our graph will look like. You'll notice that the negative 1 here is outside of the absolute value function, right? So that means we are taking our absolute value function and we are then moving it down 1. If I had a function that looked like this, f equals the absolute value of x minus 1, oopsie, there we go, x minus 1 inside of the absolute value function, right? Then this is telling me that I'm moving to the right, but I'm keeping the v. So that would look like this, right? Which is not what our function is saying. So the negative 1 is on the outside of the absolute value brackets. So that means we are shifting that v down. So we have simplified the function. We have sketched the graph of the function. What is the domain? Looking at the domain, x can be 0, it can be any positive number, it can be any negative number. Therefore, the domain is all reals. But hang on a second. Remember the definition of our composition function. In order for us to figure out what the composition domain is, we have to make sure that the x have to be in the domain of g of x, and then g of x has to be in the domain of f of x. So we have to look at each one individually. So let's erase our thoughts here. And let's take a look at the inside function. The inside function is g of x, which is the square root of x. This is not a domain of all reals. This domain is that x has to be greater than or equal to 0, because inside the square root I can only have positive numbers. And then the output of g, the range of g, what are the possible y values? Well, let's think. If we go back to lesson 1 where we did what are our basic functions, the square root function was something like that. So x has to be positive, any positive number, and y is also going to be positive. So actually, instead of writing y, I'm going to write g of x also has to be greater than or equal to 0. It starts here and goes up and to the right. So the g of x's have to be greater than or equal to 0. We are taking the g of x's and putting them inside f. So when we put it inside the f function, we only are able to have a domain where x is greater than or equal to 0 as well. Because remember, our g of x becomes our x for the f function. And I know it gets a little bit confusing when we're saying f of x and g of x and functions and notations and all of this stuff. So I really want you to focus on the idea that we're putting something into the g function. Whatever we come out of it, whatever comes out of this function, the range of g, right, will be the domain of f. Because the range of g, the output of the g function, becomes the input for the f function. So whatever the restriction on the range of g is, the same restriction will apply to the domain of f. We can talk about more details in class as well. All right, one more example here. We have an f function that is x over x minus 1, and we have a g function which is 1 over x plus 1. In A, we are being asked for f of g and its domain. Then we are looking for g of f. So I'm going to start with A. Okay, f of g of x. This means I'm going to have a numerator with something in it, because there's an x on top. I'm going to have a denominator with something in it, minus 1. And the something, the x bits, are the g of x function. So I'm putting 1 over x plus 1 here, 1 over x plus 1 here. And this is where it's going to get a bit messy. I have a stacked function, a stacked fraction. I have a fraction in the numerator and the denominator. I don't like this. I want to simplify it. So I'm going to multiply by the common denominator. And you can see that the common denominator here is x plus 1. If I multiply the top by x plus 1, and I multiply the bottom by x plus 1, I'm not really changing the function, right? Because I have same on top, same on the bottom. This is really just 1. And anything multiplied by 1 is going to give you back the same number. So this is a special case of 1. I'm choosing my fraction so that I know it's 1. I'm not changing the actual value here. I'm just rearranging what it looks like. Now, if I multiply the numerator by x plus 1, I'll get an x plus 1 on the top and an x plus 1 on the bottom. So that gives me 1 in the numerator. In the denominator, I have to multiply the bracket term and this term. There's two things here. Well, the bracket term is going to give me a 1 minus x plus 1. I'm going to simplify it further. This is 1 minus x minus 1, right? The positive 1, negative 1 cancels out. So this is just negative 1 over x. So this started off looking a little bit scary. But once we simplified using a common denominator, or a common factor, it actually turns out to be not so scary at all. Okay. So let's take a look. What are the restrictions here? Looking at g of x, we have this as our original function. What is the domain of g of x? Well, we know that we can't have a 0 in the bottom, so the domain of g of x is that x cannot be -1. And when we have a fraction with an x on the bottom that has a restriction like this actually represents a vertical asymptote. Okay, vertical asymptote means that we have a imaginary vertical line at x -1. The graph cannot touch it. So that means then we have horizontal asymptote as well. Remember that we have 1 over x is this, where we have a horizontal and vertical asymptote, and the two key points are 1, 1 and -1, -1. So this +1 means that we have moved it over by 1. We've moved it over 1. So this means in our range, what does that look like? Our vertical asymptote is at -1. Our horizontal one is still at 0. We have a horizontal asymptote at y equals 0. And we have a vertical asymptote at x equals -1. But the shape of the graph is still there. So as long as we don't touch those asymptotes, we're good. So our range here is that y cannot equal 0, which is essentially we can't be a horizontal, we can't touch the horizontal asymptote. So remember, the range of g of x becomes the domain of f of x when we have a composition. So that means the domain of f of x is that x cannot be 0, which is a good thing because we cannot have a 0 in the denominator. So we're done. We know the domain, we have simplified the function, and we're good to go. So I'm going to move over here, and I know you might not have enough space here, but you can always add a sheet into your notebook. I'm going to do B on the side here. Right. Just do it right here. Might be able to squeeze it in. All right, g of x, essentially, we have a very, very similar function here. G of x has a 1 on top and x on the bottom plus 1. And the f is x over x minus 1. X over x minus 1. So again, I'm going to choose to multiply by x minus 1 and x minus 1. Same on top, same on the bottom. So then I'm going to get g of f of x equals, I'm going to have an x minus 1 on top divided by x plus x minus 1, which simplifies to x minus 1 over 2x minus 1. So not as cute as our last one, but we can do that. So here is our composition function. Let's